Hello, good morning everyone. Today I would like to share with you a topic on quantization. What is quantization? Quantization is the process of mapping input values from a large set to output values in a smaller set. But why do we need the quantization process? This is because to find the magnitude at particular location. Okay, for example, you have the analog signal xt. Okay, this is the analog signal. Okay, at t. So this is a sinusoidal signal with the amplitude of 3. Okay, now you want to find the quantized signal. Okay, in order to find the quantized signal, you need to find the magnitude at each particular location. This is the definition of the quantization, right? And why we need it. Okay, so if you look at this figure, analog signal, we need to quantize each one. Each one, we need to quantize it. So, we want to get this signal. So, therefore, we can plot like this. This is 1, 2, 3, okay, based on the shape of the analog signal. So, this is 2. And this is 1. And then you get back a 0. Alright. And then number 7 is go down, right? Number 7 is go down. So this means this is a negative 1, negative 2, negative 3. Okay, so negative 1, negative 2, negative 3. Okay, so this is the quantized signals. It's not continuous signal anymore. For this signal, for analog signal xt, that is the continuous signal. But for quantized signal, it's a discrete signal. So it's a xqn. It's a quantized signal. So this quantized discrete time is also called a digital signal. So there are 3 types of the quantization. So there are 3 types of quantization. So the first one is the rounding. And the second one is the truncation. And the third one is the sign magnitude truncation. So for the rounding is we find the nearest quantization level. Okay, we find the nearest quantization level. And for the truncation is to find a level that is smaller than the next higher one. Okay. And for the sign and magnitude truncation is truncating smaller absolute value. And then this one is we seldom use it. Okay. So this is the graph of the type of quantization. This is the original signal. Okay, this is original signal. And then if rounding is to find the nearest quantization level. Okay, and then for truncation is to find a level that is smaller than the next higher one. Okay, and this is the sign magnitude truncation. So I will show you later how each one works. So if the improper quantization may cause to the loss of information. And the formula for the quantization is we use the L equal to 2 power of B. So this is the formula for the quantization, in which L refer to the levels, B equal to bits, how many bits of word corresponding to its quantized values. So it's a bits. So if the quantizer has 4 bits, for example. So 2 power of 4 equal to 16. So equal to 16 levels. Then another example, let's say if I have the 12 bits, so 2 power of 12 equal to 4096 levels. So this is how you use this formula, L equal to 2 power of B, to find the number of levels. Now let's look at the example. Let's consider the following discrete time signal. Xn equal to 0.9 power of n, in which n should more than or equal to 0. And if n is less than 0, you will get 0. So by following the formula given in the question, 0.9 power of n, so you assume if you want to get xt, so you assume n is t, then you substitute a value from 0 to up to, from 0, starting from 0 up to any value that you want. For example, I goes up to t equal to 8. So this is the shape of the xt using 0.9 power of t. And this is the value I obtained. Okay. For example, 0.9 power of 0, 0.9 power of 1, 0.9 power of 2, 0.9 power of 3. So this is the value. Okay. Here I want to emphasize on the truncation and the rounding method for the quantization method. So which one to choose? So just now I already told you rounding is to find the nearest one. So if 1, it still remain to the 1. Okay, and 0.9 still the same because it's the same. And then 0.89, the level should be what? What should be the level? Okay, if you look at here, we have 0, 1, 0.1, 0.2. We have this level. Okay, we already have this level. And the range, we have already the levels. So we either choose, okay, if the value is for 0.981, it's either 0.8 or 0.9 because based on the level of quantization, and then each level is increment of 0.1. So I have to base on this value, okay, from 0 to 1. Let's say this one, 0.81. So for the rounding method, is nearest one is 0.8. For quantization is a level that choose a level that is smaller than the next higher one. So I choose a smaller one. So 0.8. This is the truncation method. And for the 0.792, nearest one is 0.8. And the truncation is, okay, I choose a smaller than 0.79, that is 0.7. Similarly to the 0.65. So 0.65 is more than 6.5, so that is rounding to 0.7. But for truncation, again, is take a value lower than this one, so you have 0.6. Okay, now you understand? Okay, after that, now we go to we look at the various number representation for B. Okay, various number representation for B. Okay, this is how many bits? If you look at here is 1, 2, 3, 4, 4 bits. Okay, this one 4 bits. And then this one is for 3 bits. This is 3 bits and this is for 4 bits. Okay, there are few types. Okay, you have can be using the sign magnitude or 1 complement, 2 complements, or offset binary. So for the coding. Okay, so which one to choose? Oh, what is this? For sign magnitude, actually this is the setting that bit to 0 for a positive number. So this is a positive number, 0 to positive 7. So all the first number is 0 for the positive. And setting 1, okay, the first number is 1 for the negative number. So this is how it's worked. And the negative 0 is 1, 0, 0, 0. And then for the 1's complement, this means that the complement of is positive. This means change 0 from here, then 0 to 1. For the positive value is the same. 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1. That one is the same, positive value. For the negative value, this means that you change the 0 to 1. And change the 1 to 0. For example, so this is for 1's complement. Let's say I have positive 1. This one is equal to 0, 0, 0, 1. But the negative 1 value, what is the value for negative 1? So I will change the 0 to 1 and change the 1 to 0. So I will have 1, 1, 1, 0. Let's say I have a positive 2 value is equal to 0, 0, 1, 0. But negative 2 value is 1, 1, 0, 1. I opposite it. Okay, I change the 0 to 1 and 1 to 0. So this 1 complement has the 2 representations of 0 and 1. And then if 0 is 0, 0, 0. If negative 0, you have 1, 1, 1, 1. So there is a negative 0. So different sign from the magnitude. If sign magnitude, you have 1, 0, 0, 0 as the sign, negative 0. And next one is the 2's complement. So there is only 1, 0 represent as 0, 0, 0. Okay, 1, 0 for 0, 0. There is no negative 0 value. And those positive numbers are the same. And then for negative number, okay, this will teach you how to get this negative number. Okay, so for negative value, after the 1 from the right side, invert all the bits. Okay, for example, so first of all, I'm starting from the right, then find the first one. Okay, example 1. 0, 0, 1, 1. Okay, starting from the right, find the first one. So this is the first one. Okay, second step, invert all the bits to the left of that one. This means that, okay, once you find the one, the first one, after that, you need to change the value after that. So you have to change 1, 1, 0, 1. This last one is still remain the same as this. This is the first one remain the same, and the following all need to invert. Okay, opposite value. Okay, second example. If I have 0, 0, 1, 0, okay, where is my first one from the left? From the right, sorry, from the right. Okay, so this is the first one from the right. Therefore, I change this one and this one only. So 1, 1, 1, 0. Okay, these two I remain the same. These two I remain the same. I just change these two. Similarly to this one, when I found the first one from the right, these 3 value I will change it. Okay. Okay. The next example. If I have 0, 1, 0, 1, okay, this is the first one from the right. So this one I copy down. And others, I change it. So 1, 0, 1. Okay, I change this 3. Okay. For the offset binary, it's more or less like access or bias the interpretation. So for example, I have the binary value 0, 0, 0, 0 or 0, 0, 0, 1 up to 1, 1, 1, 1. And then for the access interpretation, this is minus 7. This means minus 7, minus 6 up to positive 7. So this is the offset access interpretation. So if you want to know what it is, this is the unsigned. If for the unsigned interpretation, this means that this starting from 0, 1 up to 15. Okay? Next is the quantization error and quantization noise. The quantization error depends on the number of levels. So if the quantized signal corresponding to a discrete signal xn is denoted by the xq. So this is the quantization error equal to xn minus xq. That is xq is the quantized signals. And then the quantization signal to noise ratio, we call it SNRQ, is defined as the ratio of PS and PN in the error. Okay, PS is the signal power, PN is the noise power. So PS equal to 1 over n summation of the xn square. For the noise is a summation equal to 1 over n equal to the summation of the epsilon square. So SNRQ equal to 10 log 10 PS over PN. Also equal to 10 log 10 summation of the x square divided by epsilon square. Next is the dynamic range. Okay, we need to know the dynamic range because we can determine what is the XD, the maximum and the minimum. So the XD or the dynamic range D is equal to X maximum divided by X minimum. And if the XD is sampled and quantized to a level using a quantizer with full scale range of D, the quantization step is defined as D over L. Okay, you need to remember this formula. Later you will use this formula to solve the question. This dynamic range is expressed in dB. Okay, this is the unit is dB. So if I have 16 bits of a quantizer, the dynamic range is 20 log 2 power of 16. That is equivalent to 96 dB. Let's say if L is large, so the error is likely to take on any value between delta, negative delta over 2 divided by negative delta over 2 to delta over 2. Delta is the resolution. So this is the probability density function of a signal quantized by rounding. Okay. Now let's look at the example. An analog signal xt equal to 2 sine 4 pi t volt is sampled at a sampling rate of 13 Hz. The signal is then being quantized and encoded into 4 bits code words. Find the discrete signal, the quantized signal at the rounding and truncation, and encoded output signal if the quantizer dynamic range is from negative 2 volt to positive 2 volt for the first 5 samples only. Okay. Now let's extract the information from the question. So xt equal to 2 sine 4 pi t. and then S equal to 13 Hertz, the sampling rate. And then number of bits equal to 4. And then the dynamic range. Dynamic range is from negative 2 volt to 2 volt. So first 5 samples only. So this is the information that extract from the question. So you need to find, okay, the question asks you to find discrete signal and also quantized signal and also the encoded output. So this quantized signal including the truncation and the rounding. Okay, so this is the information that you need to find. So first of all, what you need to do in order to solve this question, first of all, you need to know the maximum variation. Okay, the maximum variation. So D equal to X max minus X min. So in the question given to you is from negative 2 to 2. So 2 minus negative 2, you get 4. So this is the 4 volt. And then second step, what is the level? Okay, how many level? You still remember the formula? L equal to 2 power of B. And then from the question that is equal to 4 bits, right? Number of bits equal to 4. So 2 power of 4, you have 16 levels. And then step number 3, what is the quantization step? Or we call it as a dissolution. So delta equal to D over L. This is equivalent to 4 divided by 16. Okay, D is 4 because first step you get a 4. 4 divided by 16, you get 0.25 volt. Okay, step number 4, you need to create the 16 levels. Okay, you need to create. So now I have created the 16 levels. I have drawn the line of 16 lines. So you see, you count. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, here is 10. Okay, 11, 12, 13, 14, 15, 16. So it's 16 levels. So 16 levels, you need to find the location. Okay, step number 5. Step number 5 is find the location of 16 divided by 2. That is equivalent to 8. And then the location at line number 8 is negative delta over 2. And the line number 9 is delta over 2. And draw a line in between. Let's count together. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So the line number 8, you will get negative delta over 2, and line number 9 is delta over 2. Then draw a line in between. What is the value of delta over 2? Delta from the step number 3 is 0.25. So delta over 2 is 0.125. So negative, this is negative 0.125. Okay, so this is my starting point of 0. So now you go back to the question. So each of the, from the step 3, we know that each of the quantization step is 0.25 the difference. So you add up 0.25. Then what is the value? 0.375. And then add up another 0.25. You will get 0.625. This one add up again, you get 0.875. This one you get 1.125. Okay, until the end. And then this one you get 1.375, 1.625, and then this one is 1.875. Okay, similarly to the negative side. So this one is negative 0.375. This one negative 0.625, negative 0.875. This one is negative 1.125, negative 1.375, and then negative 1.625, and then negative 1.875. So you see, the range is lying in between negative 2 to positive 2. Also, you can label the code words. Okay, step number 6, you label the scale. Okay, you have done this one, label the scale. And then step number 7, you label the code word. What does mean this one? Okay, you see, just now it says 4-bit, right? So it's 0, 0, 0, 0, then 0, 0, 0, 1, up to 1, 1, 1, 1. So you have 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, and then 0, 1, 1, 1. Then this line is 1, 0, 0, 0. And then this one is 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 0, and then 1, 1, 1, 1. So this is the common binary code word. So step number 9 is draw a table, and step number 8 is draw a table. Okay, I have done the draw a table, and then you can fill in how many bits. Okay, it's 4 bits words, right? And then the question asks you for the first 5 sample only. So 0, 1, 2, 3, 4. So 5 sample. So this is referred to first 5 sample. And then discrete signal xn. Discrete signal xn. So in order to find this, xt equal to 2 sine 4 pi t. So t equal to nts. You need to know that t equal to nts. So we substitute the t equal to nts to find the discrete signal. So therefore, x nts equal to xn equal to 2 sine 4 pi nts. Okay. What is the ts? Okay, ts is 1 over s. Okay, 1 over s, s is the sampling rate. This given from the question is 13. So this will equal to 0.0769. So this is, I use the 4-point decimal. So we use this formula, x nts equal to 2 sine 4 pi nts. Okay, to fill in the table. Okay, so we have the discrete signal xn, right? So we use this formula. So I get the answer 0, 1.6456, 1.8704, 0.4803, and negative 1.3245. Okay, this is the value that I get it from here. Next, I want to do the quantized signal. XQN for rounding first. Okay. So for rounding, okay, let's move to the level here. The first one is n equal to 0. When n equal to 0, you have the value of 0. Okay, you have the value of 0. So what is the rounding? Rounding. Okay, rounding, I will use the shape of 0, and truncation, I will use the shape of cross. Okay, for rounding, I will take the nearest one. So this is, I put the rounding here for 0. Okay, and then for truncation, I will take the lowest value. So I will take this value. This is for n equal to 0. And then when n equal to 1, I have the value of, based on the calculation just now, is 1.6. Okay, 1.6 is about here. One point six four five is about here. It's not even reach half. So for the rounding, I will get the nearest one. And also for the truncation, I will take the lowest value, lowest than the 1.645. So I'll get 1.625. Also the same. And then the third value, when n equal to 2, I have the value of 1.87. Okay, 1.870. Okay, 1.870 is nearly here. Okay, and then the rounding is the nearest value. So I will get it here. And then for truncation, I will get it here. Okay. And then when n equal to 3. Okay, when n equal to 3, I have the value of 0.4803. 0.4803. Okay, so which is somewhere around here. 48. So 48, this one I divide by 2, this one I get 0.5. So not even reach half. So nearly about here only. So for the rounding, I will take here, and for truncation, also the same location. And then for n equal to 4, I have the value of negative 1.3245. Negative 1.3245. So it's somewhere around here. Okay, so if I divide by, it's somewhere around 1.3245. So it's somewhere around here. If I divide into 2, you will get negative 1.25. So it's in between. So let me draw the line first. Okay, so it's more than half. Okay, it's more than half. So for the rounding, I will go to this one, negative 1.375. And for the truncation, also the same. I will take a level that is smaller than the current one. Okay, So this is the rounding and truncation. So rounding I put as a 0 and truncation I put as a cross. So this table will be filled for the quantized signals. For 0 I get 0.125. Okay, this is because this one 0.125 is this one, and for the truncation is negative 0.125. Okay, for the truncate, so this one also quantized, but using the truncation technique. This one I will fill in for the encoded output. For the truncation. Okay, so just now this one is negative 0.125. Okay, what about the code word? If you go back, what is the code word? Negative 0.125, you have the code word of 0111. And for the 0.125, you have 1000. Okay, so I fill in 1000 and 0111. Okay, for the next one, 1.625. So when n equal to 1, I have the value of, okay, understand, 1.625. 1.625, I have the value of 1110. So both are the same. 1.625, 1110. This one also the same. Okay, next one is 1.87. When n equal to 2, okay, when n equal to 2, rounding is 1.875, truncation is 1.625, and this is the code word 1111 and 1110. So I fill out 1.875, 1111, and 1.625, 1110. And then when n equal to 3, I have the value also the same, 0.375 for both truncation and the rounding, and the code word is 1001. So 0.375, so 001. This one also the same. And then the last one is negative 1.375, code word is 0010. Both are the same. Okay, so we have complete the truncation and the rounding quantized signals. And next we can also find the quantization error. Okay, this is the extra because the question didn't ask you the quantization error, but you also can, if the question asks you the quantization error, you can use the formula. So I put as a number 10, quantization error. That is epsilon n equal to xn minus x quantized n. So this one you can use, for example, for the rounding. Okay, you can just choose the xn minus with the xq. Then you will get the answer based on the formula epsilon n equal to xn minus xqn. Let's continue. This is the noise power Pn and equal to its variance. So Pn equal to the variance square or equal to the resolution square divided by 12. And the RMS quantization error is given by this. delta divided by 12, square root of 12. So with delta equal to d over L, some computations can be done by 10 log Pn or equal to 20 log divided by minus 20 log L minus 10.8. So this is the statistical estimate of the SNR in dB is given by this one. And while this one is the for a B quantizer with the number of level like this, the statistical estimate is given by 10 log PS plus 10.8 plus 6B minus 20 log D. Now let's look at an example. A sample signal that vary between negative 2 volt to 2 volt and is quantized using B bit. What is the value of B will ensure an RMS quantization error of less than 5 millivolt. Okay, in order to solve this one, a full scale range is D is given negative 2 to 2, so D is equal to 4 volt. And the RMS quantization error is sigma equal to resolution divided by square root of 2. So resolution also equal to D over 2 power of B. So 2 power of B, you get D divided by sigma square root of 12. So this will equal to 220.94. So when you log it, and then you will get B equal to 8 bits. Okay, B equal to 8 bits. So as a conclusion, this is the block diagram of the digital processing of analog signal. Analog signal processed through a sampling process to obtain the discrete time signal. And then quantization to get a staircase signal, then coding process to obtain the digital signals. Similarly, for digital to analog conversion, when you get a digital signals, okay, you decode it, you pass through a decoder to get a discrete time signal, and then from there you get, after you pass through a whole circuit to obtain a quantized signal. So from a quantized signal, you pass through an analog pulse filter to get the analog signal. So this is how from the analog to digital and digital to analog again. So that's all for the quantization topics, and hope you can understand and enjoy your watching. Thank you.